Hello, welcome to another video. This is going to be lesson 11.1, which is sort of a brief introduction to conics with an exploration of ellipses and hyperbolas. So now in class I take a lot more time to talk about these shapes, where they come from and things like that. So I'm going to be leaving some links in our Schoology page just to some other videos that really explain where these shapes come from, how they're constructed, blah, blah, blah. Because me on my iPad on a two-dimensional thing with only my pencil, there's only so much I can really show you. There's some really great videos out there that have great visuals or demonstrations or, just modeling and things like that, or computer graphics that just would really convey this better than I can, okay? So I will leave those linked in Schoology, so keep an eye out for those. I'll title them accordingly. So, if you want to see how is an ellipse constructed, right? How do I do that? You can just check our folder, okay? Now, I will briefly talk about these, but just know that this video is not very sufficient for the intro to conics. It's more just the graphing ellipses and hyperbolas. That's really what I'm going to be focused on in this video. Anyway, so a conic section is a curve. I'm reading this part right here. Right here. It's a curve formed by the intersection of a plane and a double cone. So what happens is so if I take a double cone, what's it called, right circular cone. All right, something like this. It looks like an hourglass, right? Well, if you cut into this, so imagine taking a plane, meaning a flat surface like this, right? If I cut, say, horizontally into this cone, then I get a shape here from the cone. And that shape is going to end up being a circle. So when you cut flat horizontally into the cone, you get a circle. I can erase this. Okay, see, this is already why the limitations of my iPad. If I cut diagonally a little bit, something like this maybe, then I get a sort of elongated circle, which we are going to call the ellipse, right? And then if I make a cut that's sort of, it's still diagonal, but it kind of goes through the edge of the cone like this. This is going to end up making how do I even draw this? A parabola. Okay, so the parabola actually comes from here. And then same story, if I make a vertical slice, so I cut it kind of like this, vertical plane, this is going to end up creating what's known as a hyperbola. Am I even drawing this right? That's supposed to be pointed the other way. It's like this. This was like this. I don't know. I'm not the best drawing this, really. I'm terrible at it. So please go check out those videos for a way better demonstration of how this double cone is cut to see these images. Okay. All right. So that's all. That's the intro and whatever. Last thing I'm going to say though is that these are quadratic relations. Relations because we're not dealing with functions here necessarily. Notice all of these shapes. The circle fails the vertical line test. Ellipse fails the vertical line test. Parabola here passes it, but we're going to see sideways parabolas. That fails the vertical line test. And so does the hyperbola, right? So we call them quadratic relations. Quadratic because the equations are of second order, meaning exponents of 2. But these aren't really functions. Okay, so don't say that, the hyperbolic function. Now that means something else. Okay, that's something else. Okay. Now, each of these conic sections we can write in, I'm going to do this in red here, general form. Using the equation, here's general form. It's kind of long. It's ax squared plus by squared plus cx plus dy plus e equals 0. Set that equal to 0. And yeah, it looks complicated, but look, all it is you have a quadratic x term. You have a quadratic for the x's, you have a quadratic for the y's, and then you have some constant e, right? We set that equal to 0. Now we can rewrite each conic section in standard form, which we're going to see throughout the video, by doing a process that's known as completing the square, which, hey, we should know what that is, right? We did that in the fall semester of Algebra 2, where we completed the square. So I'm not going to cover it in this video. I probably will make a short video within this unit that's a reminder. But if you want the full-blown teach on completing the square, hey, go visit back to Unit 4, I think it was. Unit 4 is when we were doing completing the square. Okay, so check out those videos. Okay, so let's talk about ellipses. So what is an ellipse? An ellipse is a plane curve surrounding two focal points such that for all points on the curve, the sum of the two distances to the focal points is constant. Now, see, with me on my iPad, I feel limited in really demonstrating this, and that's why I want you to check out those videos. But I'll try to explain it here as best I can. Taking a look at this ellipse that's down here, notice what I've labeled here is a center point and then these two focus points, which we call foci. Foci for plural for focus. Now, the thing about the ellipse is if you pick any point on this ellipse, right, just let's say you pick that point, then the distance, I'm going to call this distance 1, the distance to the first focus added with the distance to the second focus, that sum of those distances is held constant no matter where you are on the ellipse. So, you know, if I pick somewhere, just like right here, right, and I look at this distance, so D1 has become longer, but D2 has become a little bit shorter. So what this says is that the red, D1 plus D2, is equivalent to the blue, if that makes sense, okay? The sum of those distances doesn't change. Of course, D1 and D2, right, they grow, they shrink, whatever, but together, that length doesn't decrease or increase. It stays constant, okay? And this is what defines an ellipse. You know, if you think about a circle is a center point where any point on the outer edge, any point, they are all the same distance r, being radius, from the center, right? Every point on a circle is equidistant from the center. So, you know, that's what's held constant. An ellipse is a more general definition where it's not necessarily that the distance between the center and the edge is held constant, but this idea of these two foci and their distances, that is what's held constant. So I hope that helps. But I do recommend checking out the video I've linked in Schoology. It's basically a guy who takes two nails and he nails them into a board, and then he takes like a string, right? And then he takes the string and he just moves it along and he traces out an ellipse. And you can really see how the length of the string doesn't change as he creates that ellipse. And I think that's a really good demonstration. So sorry I can't show you here. Okay. All right. C, what is that? Okay, C is the center of the ellipse. So we're going to denote that as the ordered pair H comma K. H comma K is pretty much going to be the center for all these objects. For parabolas, it's still going to be the vertex, though. F1 and F2, they are called the foci. So singular, this is focus, all right? But plural, we call that foci. I guess some people say foci, but I don't know. I like foci. Okay, longest diameter of the ellipse is called the major axis. And the endpoints on this axis are called vertices. So I'm going to go here to my little ellipse, and I'm going to do this in red here. This length, this diameter extending from one end to the other, that is the major axis. And these endpoints on the major axis that meet where the curve is, those are our vertices. This is vertex, and that is also a vertex. I'm going to switch colors here so we can, because I can do that. Now, the shortest diameter, well, if major is the longest, then minor would be the shortest diameter of the ellipse. And the endpoints on this axis are called co-vertices. So they're basically vertices, but they're not the main ones, right? So I've got my co-vertex here joined, through this diameter, like so. I want that to go right through. Can I make it do that? Can I make it go right through? Beautiful. Okay. So there's my co-vertex. There's my other co-vertex. Co-vertex. Nice. Okay. All right. And now I'm going to have letters A, B, C, which are part of standard form equation. So we're going to get to that, the standard form. But to talk about what those letters mean, I'm going to do this in yellow. A is the length from the center to the vertex, which means so if I measure from this center to all the way over here to this vertex, right, that is the length A. B is the length from the center to the co-vertex. So it's just the shorter length. Like so. That length is B. And then finally, C is the length from the center to, can you guess, the focus. Yeah. So this length from the center to the focus, like so. That length is C. Okay? I hope that makes that clear. All right. You know what? I think I would like it better if I put C here. See that? Ooh. Nice. That's C. Okay, I like it. Good. Okay. So moving on to the standard form equation, kind of talking about this for a second. I'm going to zoom in here so you really see it. I'm not going to have you memorize these. When we do eventually take our quiz on this, what I'm going to do is let you make a cheat sheet. So you don't have to memorize it, but I'm not going to give it to you, if that makes sense. So you're going to make a cheat sheet, and you'll have to decide what you want to write down. So a horizontal ellipse, this means it's a horizontal orientation. It looks like this, right? Maybe I should make it more elliptical and less pointy. Ooh, that's much better. Actually, I don't even know why I'm doing that because my little pen, yeah, there it is. Look, it makes a perfect one. Why am I even doing that? Okay, anyway. So a horizontal ellipse versus a vertical ellipse, right? Here's my horizontal, and then the other one's my vertical. Where's my lasso? There's my lasso. Boom. Okay. Now, if you're comparing these equations, right, remember, h comma k is what we're calling the center of the ellipse. So that's referring to these h and k values. This a and this b value, well, if it's horizontal, it looks like we're putting a underneath the x term. If it's vertical, we put a under the y term. And this is because since a is the distance, A is the distance from the center to the vertex. So if the major axis, right, because the major axis is the axis from both vertices, right, from here to here. That's the major axis, which I've done in red, right? If your vertices are there, then, oh my gosh, I'm doing such a terrible job. You probably totally understand what I'm saying. It's x because your vertices are horizontally, like over here. They're A horizontally, it's associated with x. A vertically would be associated with y. Okay, I hope that was better. I feel like I totally just terrible. I would note that A is always more than B. In particular, A squared. I might star this. I might say star. A squared is always more than B squared. Is always. Okay, so basically the bigger one goes, whichever one is bigger, that tells you that's the major axis, is either horizontal or vertical. Okay? All right. I'm going to redraw these ellipses and move on. Boop. And boop. All right, let's move on. And by the way, notice with standard form, you don't see C, right? You see A and B, you see H and K, but you don't see C. So what is C? It's that length from the vertex to the focus, and you can use this equation, C squared equals A squared minus B squared, to find it. Where does that, you might notice, hey, isn't that like Pythagorean theorem? And yeah, it is. A squared equals C squared plus B squared. This is a Pythagorean thing that comes up through the geometry of an ellipse. Okay? If you want to, you can think about that or go look up a video about that. I'm not going to talk about it here. But yes, that equation comes from Pythagorean theorem, dealing with triangles and all that business. Okay. Okay, so let's look at some graphing examples. These are pretty quick. All right. So let's graph an ellipse generated by this equation, and we'll list all of its key features. So first of all, I see that A squared and B squared, right? Well, which one's which? Well, A squared is the bigger one, so A squared is 25. And because A squared is under Y, that makes this a vertical ellipse. Okay, so we're going to say vertical. Ooh, I don't want you to get confused to say that's overt. Say a vertical ellipse. And I know that because of Y. Okay, because the bigger one is underneath Y. And so B is 16. So naturally, I can conclude that A is 5, and of course B would be 4. And since C squared equals A squared minus B squared, then C squared equals 25 minus 16. You should know what that is. That's 9, which means C is 3. Okay, so I would find your ABC first because that's going to help you figure out all of these things. Okay, so ask ourselves, where's the center? Well, the center is H comma K, and that comes from X minus H squared and then plus the Y minus K squared. So if I look at this, it says X minus 3 squared. That means H is 3. And then it says plus Y squared. That means it's Y minus 0. So it's 3 comma 0. So that's my center, is 3 comma 0. I could just see it plainly right there. Okay. So I'm just going to do that. I'm going to put my point right here. 3 comma 0. All right, where are my vertices? Where are they? My vertices? Well, my vertices, you remember you say they are away from center. And since it's a vertical ellipse, we're going to say vertically. So A is 5. I see over here, right? A equals 5. So since A equals 5, we have 2 points. The first vertex we're going to add to the Y value 3 comma 5, and the other one 3 comma negative 5. And those are your vertices. So 3 comma 5 and 3 comma negative 5. Those are my vertices. My covertices, right? Well, since B equals 4, we're going to add and subtract 4 from the X value of the center. Oh my gosh, I hate writing. Oh my gosh. Oh, I cannot. I need to zoom in. I wish I had beautiful handwriting. I sometimes get sad about it. I don't like my handwriting all the time. Be away horizontally. You say, it's okay, Mr. Spake. I say, I'm sorry. 7 comma 0 and negative 1 comma 0. That's 4 away horizontally. So negative 1 comma 0 and 7 comma 0. And now that I have those points, I can sketch the ellipse. We're going to put the foci here, but this is your criteria for an ellipse. You just need all the vertices. Okay, now I haven't tried this with my little pencil here. I'm very curious if I just roughly draw an ellipse. Ooh. Oh, oh, can I make it fit? Can I make it fit? Kinda. It's okay. It's not perfect, though. I'm going to try it one more time. I'm going to just see if my iPad can handle it. Whoop, whoop. Nah, it's okay. I'll just sketch it. All right. We're just going to sketch it. And so you're going to just sketch the ellipse. So, I mean, guys, you can literally scroll forward right now. I don't really care. Or you can keep me company as I sketch this ellipse around, as I try my best to keep that elliptical shape. Now, it doesn't have to be perfect, but it needs to be very clear that what you're drawing is indeed an ellipse. So I'm not going to be incredibly picky, because this isn't an art class or anything like that. However, if you get lazy with this, I am taking points off. Meaning, if you just, there it is, there's my ellipse. No way. Are you kidding me? That's not an ellipse at all. Do not be lazy with that. Oh my gosh. Absolutely not. Unacceptable. Please, no. Okay? You see what I've drawn in yellow? That is not an ellipse. I don't know what that is. It's not a square because it doesn't have right angles. It's not a rhombus. It is crap. That is what that is. That is nonsense what that is. Okay? So please, please, please draw an ellipse. It's okay if it's not perfect, right? Maybe you trace around and then, you kind of fumble this a little bit and it's like, okay, it looks a little bit like an egg, a messed up egg, a bad chicken egg, but it's close enough, I guess, right? But please just try to keep that ovular shape, all right? Just come on. We can do that, right? We can do that. It's not asking that much. All right, and then the foci, the foci also lie on major axis, right? So you can say these lie on major axis. So C away vertically, because the major axis was vertical, right? And that C away, that was 3, right? C equals 3. So we're going to say 3 up from the center and 3 down. 3 comma 3 and 3 comma negative 3. All right, 3 comma 3, 3 comma negative 3. Also, personally, I like to notate the foci F1 and F2. It doesn't matter which one you call which. 1 and 2 don't matter. And then I'm just going to put them here on the graph. I just like that. It really tells, whoever's reading this graph, it clearly indicates that is the focus, right? Those are the foci. Okay. All right. In the interest of this video, I'm really not going to do example 2 because it was classwork practice. It was just more. The key will be up in Schoology. No reason to make this video longer than it needs to be, right? So, whatever. We're just going to go ahead and skip this one. That's how you graph it. And you can check out the key on Schoology, okay? All right, let's move on to hyperbolas. Because I want this video to be short as I can. Hyperbolas. A hyperbola is a plane curve generated by 2 focal points, same setup as we were talking about, such that for all points of the curve, the sum? No. This time, it's not the sum, it's the difference. The difference of the distances to the 2 focal points is held constant. So, this one's a little bit harder to explain, because sum, you just put the lines together. But, it's the same idea. If I take this point on the hyperbola, I call this distance 1, and I call this distance 2. If you subtract, you do d2 minus d1, and you whatever that distance is, and then I'm going to pick another point. I'll pick one way over here. Then this will be my d2, and this will be d1, right? And then I do this d2 minus d1. Well, this one is shorter, so that's going to end up being negative. So what we do is that we actually end up taking the absolute value of these, because what we care about is the length, the magnitude of it, right? Not so much whether it's positive or negative. And you will find that these two things are equal. These two are equal. So no matter these points on the hyperbola, they are generated from this fact of keeping the difference constant. All right, that was a little bit harder to visualize, and I will link some videos in Schoology for you to check out that are just excellent explanations on that. All right, so things about hyperbolas. Each branch on a hyperbola has two arms, which become straighter further out from the center of a hyperbola. As you can notice, this arm is bending, but now it's getting straight here, right? It's straightening out, and this is because these arms, especially these diagonally opposite arms, so like this arm and this arm, are both approaching this line. Similarly, this arm and this arm are both approaching this line, right? And so what do we call those dotted lines, those lovely dotted lines that we see? We call those asymptotes. So these are asymptotes. And so thus there are two asymptotes we care about, and they both intersect at what we know as the center of the hyperbola. Now the center isn't a point on the hyperbola, it's a center between the two branches of the hyperbola, all right? So we call that the center of symmetry because it's symmetrical about that point. Okay. And one thing to note is that the slopes of these asymptotes are going to differ depending on if the hyperbola opens horizontally or vertically. So we have some equations for the slopes of the asymptotes, or rather the equation, but it's not a big deal. You'll see when we work it out. It's very easy to find the slope as long as you draw the picture. Okay? Okay, a hyperbola has two axes of symmetry, so kind of like how the ellipse has a major axis and a minor axis. The hyperbola has what's known as a transverse axis and a conjugate axis. So that's what goes in those blanks there. Now, the transverse axis of symmetry is kind of like the major axis of an ellipse. It's the one that has the vertices and the foci, all right? The conjugate axis is the one that separates these two branches, and it has the co-vertices, all right? You say, why don't we still use the words major and minor here? To be honest, I don't really know why it's called transverse or conjugate. I don't actually know why it is. Bad math teacher moment. I need to look that up for myself. I don't know why it's called that. But I can tell you that the transverse axis is not always bigger or longer than the conjugate axis, okay? So, you could have a hyperbola that's really squeezed tight here, but, its conjugate axis is really long, or vice versa. You have a really separate thing where the conjugate is super tiny. It doesn't, right? This can vary. So we don't really use the words major and minor because one's not necessarily always bigger than the other. Now the definitions or interpretations, of A, B, and C are all the same. So this distance from the center to the vertex right here, that's my vertex, right? This distance is A, and then you're going to have a co-vertex out here. I think, I'm going to sketch it real quick just to eyeball it. It's about right there. You say, how does Mr. Spake know where that is? I will tell you later. That distance is B, and then this distance from this focus, right? This distance from here to here, that distance is C. Okay? There we go. That's C, that's A, and that's B. Okay, I hope that's clear. All right? Also, I am bothered by the way vertex is so sloppily written there. Vertex. All right. Okay, and then as for the standard form of a hyperbola, it's very similar, to the ellipse. If you compare this to the ellipse, it's basically the same thing. It's just instead of it being plus, it's a minus because it's the difference, right, rather than the sum of those distances, which is kind of why you have a plus there for ellipse and a minus there for hyperbola. You do need to remember that distinction. Now, sadly, our understanding of A is always bigger, sadly, that doesn't transfer here. A is the distance to the vertex, but now we're saying that there isn't a major and minor axis, so can A be bigger than B? Yes. Can A be smaller than B? Also, yes. Can A and B be the same thing? Yeah, I think so. So sadly, you can't transfer that knowledge here, but most of the stuff you can. Now, if it opens horizontally, that means this way. Okay, the point of symmetry is in the center, and it opens outwards to the left and the right. Opening vertically means it's going to open up and down. Okay, and if you notice, the only difference here, right, is when it's opening horizontally, x is positive, y is negative. When it's opening vertically, y is positive, x is negative. Okay? You're subtracting x for vertically, or you're subtracting y for horizontally. I would just pay attention to say which one's positive. Whichever term is the positive one. If vertically it's positive, then it's vertical, right? If the y is positive. And then again here, this is how you find C. It's different, okay? The last one was C squared equals A squared minus B squared. For hyperbolas, it's A squared plus B squared. So it is that Pythagorean theorem that you know, okay? So there it is. Okay, alrighty. Let's do an example of a hyperbola, and then we'll be done with this video. Okay, so example 1, we're going to graph this hyperbola. Immediately, we are going to identify ABC. So what is A equal to? What is B equal to? Well, A squared equals 16, and B squared equals 9. That tells me A equals 4, and B equals 3. And how did I know that 16 was A? Well, look at this. A is over whichever one is positive. And so I noticed that it was x squared was positive, right? So that one was the A value. And by the way, since A squared since it's x is positive, y is negative, that means it's going to open outwards like this. So my hyperbola should look like that. If it doesn't look like that, I've done something wrong, right? And so you've got your A squared and B squared. Therefore, C squared equals A squared plus B squared. So it's 16 plus 9, which is 25, which means C equals 5. Okay? All right. And by the way, these numbers won't always be pretty, but they are today. Okay? Today, they're Pythagorean triples. They're nice. All right, so where's the center? Well, the center is at -1, 5. This is, again, if you're doing x minus h squared, and you're looking at x plus 1 squared, or you're doing x minus -1 squared, right? That's what h is. So h is -1. And then the same idea, if you're doing y minus 5 squared, it's y minus k. And so k is 5. So there you go. So that's the center. And I'll put that -1 comma 5 right here. Vertices. Well, the A is the distance from the vertex, and it opens horizontally. So we're going to go 4 to the right and left. 4 right and left of center. So 4 to the right would be 3 comma 5, and 4 to the left would be -5 comma 5. So -5 comma 5 is here, and 3 comma 5 is here. And those are my vertices. My co-vertices, that's B, so that's 3. So it's 3 up and down of the center, because it's B. A equals 4, B equals 3. So we're going to go 3 up, that's -1 comma 8. And 3 down, that's -1 comma 2. So -1 comma 8 and -1 comma 2. Like so, those are the co-vertices. And then we're going to get to the foci in a second. But now you need to draw the hyperbola. And you might say, well, wait, how do I do this? Because it's going to look like this, right? Well, how do you know if it looks like that, or if it's sharp like this, or if it's long like this? How do you know? And you need that to be accurate. Well, where that line goes depends on the asymptote. So what we need to draw is the 2 asymptotes, because the branches, the curves, each leg of the branch approaches these asymptotes. So you say, how are we going to do that? Well, I'm going to make a little box. And you say, what is this box, Mr. Spake? I say, I'm making a box from the co-vertices and vertices. And what this box is going to do is help me graph the asymptote, because the slope of the asymptote is rise over run, being rise is up B and run is over A. Now see, look, if we switch this around and this length was A and this was B, it would be the same thing. So your slope is always either going to be B over A, or it's going to be A over B. I wouldn't bother memorizing which is which. I would just make the picture and figure it out that way, okay? I'm going to use the back arrow on this so I get rid of those red lines. Okay. So what is my asymptote? Well, it's a little hard for me to do on the iPad, but you want to draw a straight edge just from the center through the corners. Okay? That's going to be your asymptote. Now do extend that. Don't just do it there. Extend this as straight as you can. It's preferable that you use a straight edge. Okay, so try and find a ruler or something like that. I need more rulers in my classroom. But there's my asymptotes, right? That's my first one. And then I'm going to draw the next one. Kind of like this. I'm just trying to be as accurate as we can. And this one goes like that. Okay, so those are my asymptotes, right? I don't really need arrows on them, I guess. And so now the curve that I'm drawing, it's going to approach these asymptotes. Okay, there's my arrow. This curve goes from the vertex and just approaches these asymptotes. Okay, I'll do the same thing over here. So the sequence of it all was get your vertices first, then use the vertices to sort of make a box, and all the box is for is to help you draw your asymptotes. That's it. You don't have to keep the box. If you want to erase the box or whatever, that's fine. Or, you know, if you don't even want to draw the full box, you just want to find these corner points, right? Maybe you just want to find the corner point and then this corner point and then just draw. Hey, that's fine. Okay, I don't care. But I like the box. Okay. And there it is. That's your hyperbola. We do need the foci real quick. The foci are on the transverse axis. So this is c equals 5 left and right of center. So that's just one more than the vertices. So I should have 4 comma 5 and negative 6 comma 5 by subtracting and adding 5 to negative 1, which means my foci are going to be right there. Okay, I'm going to call this F1 and I'll call this F2. So this is F1 and that's F2. Okay. And then your asymptote equations, well, it's, do you remember point slope form? Okay, so point slope form, you can write it in point slope form. I'm not going to grade picky on this. I just want to make sure you got the slope and the point, okay? It's y minus y1 equals m times x minus x1. That's from Algebra 1. Now, the point that both slopes go through is the center, right? Both asymptotes go through the center point. So you're going to use that as your point in point slope form. And then the slope, m, is just rise over run. So this is up 1, 2, 3 over 1, 2, 3, 4. And the other one is down 1, 2, 3 over 1, 2, 3, 4. So that means you have two slopes. Both are 3/4, but one is positive and one is negative. So you can actually just sum this up and say it's y minus y1 is 5 equals plus or minus 3/4, because it's positive or negative, x minus x1, but that's minus negative 1, so it's x plus 1. And that, I think, is sufficient. Look, if you really want to solve for y, you can add 5 over, and if you want to distribute the 3/4, you can, but that's good enough for me, guys. It's fine. Leave it in point slope form. I don't mind, okay? It's good enough. And there you go. There's your hyperbola. All right. Thanks for watching. Hope the video was helpful. It's really just a guide on graphing. It's not the best intro to conics. Either check out the videos that I've got up in Schoology or just come see me outside of class to talk about it if you were absent or whatever. Okay? I do have some videos from last year on this. I guess you could check those out. I don't remember what their quality is like, though. They might not be the best, so I don't know. Up to you. Anyway, there it is. Have a good night, and I'll see you around.